Welcome to today's session. We're diving into LeetCode problem number 387, first unique character in a string. This problem focuses on string manipulation and efficient data structure usage. By the end of this lesson, you'll be equipped with multiple approaches to tackle it effectively. Let's get started. The problem asks us to identify the first non-repeating character in a given string S and return its index. If there is no such unique character, we return -1. The input is a single string containing only lowercase English letters, with a length ranging from 1 to 100,000. The output is an integer indicating the index of the first unique character, or -1 if all characters repeat. Let's look at an example. For the string S equals LeetCode, the output is 0, because the first unique character is L, which appears only once at index 0. To understand further, consider another example where S equals LeetCode. Here, the output is 2 because the first unique character is V, which only occurs once in the string and is found at index 2. Now, in contrast, think about a string like S equals ABG. In this case, there are no unique characters at all, as every character in the string repeats. Therefore, the output is -1, indicating the absence of any non-repeating characters. Looking at the constraints, the string length can be as large as 100,000 characters, so our solution needs to be efficient. The string only consists of lowercase English letters, meaning characters range from A to Z. Let's also consider some edge cases to ensure a comprehensive understanding of the problem. For instance, in a string where all characters are the same, such as S equals AAA, the output would be -1 because there are no unique characters. On the other hand, if the first character is unique, like in S equals ABAC, the output is 1 because B is the first unique character, found at index 1. Similarly, for a single character string, such as S equals Z, the only character is unique, so the output is 0. Finally, let's examine a case where the unique character appears at the very end of the string. For example, in S equals OB, the first and only unique character is B, appearing at index 3. These examples and constraints give us a solid understanding of the problem requirements and the scenarios we need to handle when designing our solution. To solve the problem of finding the first unique character in a string, we can start with a brute force approach, which is the most straightforward method. Here, the intuition is simple. For each character in the string, we iterate through the entire string again to count its occurrences. The first character with a count of 1 is our answer. The steps for this are as follows. First, take each character in the string and then count how many times it appears by scanning the entire string again. If a character is unique, meaning its count is 1, we return its index. However, the main downside of this approach is its inefficiency. Since we have nested loops, one to check each character and another to count its occurrences, the time complexity is O(n squared). On the bright side, this approach uses no extra space, making its space complexity O(1). While simple to understand, this method becomes impractical for large strings, especially if the input size reaches up to 10 to the power of 5 characters. The brute force approach, while easy to implement, comes with significant trade-offs. It is extremely slow for large input sizes, and its inefficiency makes it unsuitable for strings with lengths in the hundreds of thousands. A more efficient alternative is the hash map approach. The intuition behind this method is to leverage a hash map to store the frequency of each character. This allows us to count occurrences in a single traversal and then find the first unique character in a second traversal. The steps are as follows. First, traverse the string and build a frequency map where each character is a key, and its value is the count of occurrences. Next, iterate through the string a second time and check the frequency of each character using the map. The first character with a frequency of 1 is our answer. This method improves the time complexity to O(n), as there are only 2 linear passes over the string. However, it does require O(n) additional space to store the hash map. The hash map approach is efficient and relatively easy to implement, but it does come with slightly higher memory usage due to the additional data structure. To further optimize, we can use an improved version called the optimized hash map approach. Instead of storing character frequencies, we store the first index of each character in the hash map. This eliminates the need for a second pass. Here's how it works. As we traverse the string, we build a hash map where each key is a character, and the value is either its first index or a special marker, such as -1, if the character is a duplicate. After processing the string, we scan the hash map to find the smallest index associated with a unique character. This approach retains the O(n) time complexity, as it still involves a single traversal, and the space complexity remains O(n) for the hash map. By reducing the number of passes, it achieves optimal efficiency while maintaining clarity. The optimized hash map approach is a great improvement in terms of time efficiency, but it uses the same amount of memory as the standard 2-pass hash map approach. Another alternative, specifically tailored to this problem, is the array-based approach. This method leverages the fact that the input only contains lowercase English letters, meaning we can use a fixed-size array of 26 elements instead of a hash map. Each index in the array corresponds to a letter, and we either store its frequency or the index of its first occurrence. The process involves 2 steps. First, traverse the string to populate the array with the required information, and second, scan the array to find the first character with the desired property. The time complexity remains O(n) due to the single traversal, but the space complexity is effectively O(1) since the array size is constant at 26. While more memory efficient than hash maps, this approach is less flexible, as it relies on the input being constrained to a fixed character set. After considering the various approaches, the chosen strategy for this problem is the hash map approach with 2 passes. This method strikes a balance between simplicity and efficiency. While the optimized hash map and array-based approaches offer slight performance improvements, the differences are negligible in practical scenarios. The 2-pass hash map solution is intuitive, easy to understand, and widely applicable to variations of this problem. Key observations that led to this choice include the efficiency of managing character frequencies with a hash map and the realization that nested loops are unnecessary. By counting occurrences separately and checking them later, we can achieve an O(n) solution. Although the hash map approach uses slightly more memory compared to the array-based approach, it offers greater adaptability, especially for problems with different or larger character sets. The brute force approach, on the other hand, was rejected due to its poor scalability and inefficiency for large inputs. This strategy provides the best combination of simplicity, efficiency, and adaptability, making it the most suitable choice for solving the problem. By utilizing a hash map for frequency counting and leveraging a 2-pass approach, we ensure that the solution is both time-efficient and easy to implement. This balance between performance and clarity is critical, especially when solving problems with real-world constraints or preparing for coding interviews. To solve the problem of finding the first unique character in a string, we start by understanding the goal, identify the first character in the string that appears exactly once and return its index. If no such character exists, the algorithm should return -1. The first step is input validation. If the string is empty, there's no unique character to find, so we immediately return -1. Next, we create a hash map, or dictionary, to store the frequency of each character in the string. This is done by iterating through the string once. For each character, if it already exists in the hash map, we increment its count. If it doesn't exist, we add it with an initial count of 1. This ensures that we have a complete frequency count of all characters in the string in a single pass. Once the frequency count is complete, the next step is to find the first unique character. To do this, we iterate through the string again. For each character, we check its frequency in the hash map. If the frequency is 1, that means this is the first unique character, and we return its index. However, if we complete the second iteration and no character has a frequency of 1, it means there are no unique characters in the string, so we return -1. The algorithm outputs either the index of the first unique character or -1 if all characters are repeated. This 2-step approach ensures clarity and efficiency in solving the problem. There are a few key insights that make this algorithm both efficient and reliable. First is the use of a hash map to store the frequency of each character. This allows us to check the frequency of any character in constant time, O(1). The 2-pass approach is another important factor. By separating the frequency calculation and the search for the first unique character, the algorithm remains both efficient and easy to follow. We also account for edge cases, such as an empty string, where we immediately return -1. If the string has no unique characters, like Abe, the algorithm will correctly return -1. For a string where the first character is unique, such as ABCD, we return the index 0. Additionally, if the input includes mixed cases, such as ABCC, we ensure that uppercase and lowercase characters are handled distinctly, assuming the problem is case-sensitive. The choice of data structures plays a crucial role in the algorithm. A hash map is the primary data structure used to count the frequency of each character, offering efficient lookups and updates. The string itself is iterated twice, once to populate the hash map and once to find the first unique character. When analyzing complexity, the time complexity is O(n) for building the hash map and another O(n) for the second pass, resulting in an overall time complexity of O(n). For space complexity, the hash map requires O(k) space, where k is the number of unique characters in the string. For lowercase English letters, the maximum value of k is 26. In the worst case, where all characters in the string are unique, the space complexity is O(n). This combination of time and space efficiency makes the algorithm suitable for large inputs. To better understand how the algorithm works, let's walk through a couple of examples. For the input LeetCode, we first build the frequency count. After the first pass, the hash map looks like this: L1, E3, T1, C1, O1, D1. In the second pass, we check each character's frequency. The first character, shell, has a frequency of 1, so we return its index, which is 0. Now consider the input egg. After the first pass, the hash map is A2, B2, C2. In the second pass, we find that no character has a frequency of 1, so the algorithm returns -1. These examples demonstrate how the algorithm handles both cases with and without unique characters effectively. There are a few optimizations to consider for this algorithm. If the character set is limited to lowercase English letters, we can use an array of size 26 instead of a hash map to save space. This is possible because each index in the array can directly correspond to a specific letter. For scenarios involving real-time streams of strings, we can explore sliding window or streaming algorithms that dynamically maintain the frequency count as new characters are processed. These optimizations can further enhance the algorithm's utility in scenarios with specific constraints or real-time requirements. This implementation solves LeetCode problem number 387, first unique character in a string, by efficiently identifying the first character in the string that appears exactly once. The solution involves two main steps. First, we traverse the string to calculate the frequency of each character using a dictionary. This allows us to keep track of how many times each character appears. The dictionary stores characters as keys and their corresponding counts as values. This step has a time complexity of O(n), where n is the length of the string. Second, we iterate through the string again, but this time we check the count of each character in the dictionary. If a character has a count of 1, it means it's unique, and we return its index. This ensures that we find the first unique character in the order of appearance. This step also has a time complexity of O(n). If no unique character is found after traversing the string, we return -1 as specified in the problem statement. The overall time complexity of this solution is O(n), and the space complexity is O(1), since the dictionary's size is bounded by the number of unique characters, at most 26 for lowercase English letters. This makes the solution both efficient and easy to understand. This is the Java implementation of LeetCode problem number 387, first unique character in a string. The logic mirrors the Python solution. We use a hash map to count the frequency of each character in the string and then iterate through the string to find the first character with a count of 1. The key differences include type declarations required in Java, the use of hash map instead of a dictionary, and the explicit conversion of the string to a character array for iteration. To solve this problem, we start by initializing an empty dictionary called char_count. This dictionary will be used to store the frequency of each character in the string. As we iterate through the input string s, we update the dictionary with the count of each character. For example, when we encounter the first character L, we add it to the dictionary with a value of 1. The next character is E, which is also added with a count of 1. When we encounter E again, we increment its count to 2. This process continues for each character in the string until we have the frequency of all characters. After building the frequency map, we then iterate through the string again, checking the count of each character in the dictionary. The first character with a count of 1 is our answer. In this case, the character L at index 0 is the first unique character, so we return 0. Here, the output for the first example is 0. Now, let's look at another example where the input string is LeetCode. We follow the same steps as before. First, we initialize an empty dictionary char_count. Then, we count the occurrences of each character in the string. Starting with L, we add it to the dictionary with a count of 1. Next, we encounter O, V, and E, each of which is added with a count of 1. When we encounter L again, its count is updated to 2. Similarly, the count of E is incremented to 2, and then to 3 as we process more E characters. By the time we've read through the string up to this point, the dictionary contains the counts for all characters we've seen so far. After completing the frequency count, the dictionary now includes additional characters like T, C, and others, and their counts are updated as we process the string further. For instance, when we encounter O again, its count becomes 2. After processing all characters, we move to the next step, which is to iterate through the string and check the frequency of each character in the dictionary. Starting at index 0, the character L has a count of 2, so we move to the next character. At index 1, O also has a count of 2, so we continue. At index 2, the character V has a count of 1, making it the first unique character. Therefore, we return the index 2 as the output for this example. In the final example, the input string is AB. Again, we initialize an empty dictionary to count character frequencies. As we process the string, we add A with a count of 1, then increment its count to 2 when we encounter it again. Similarly, we add B with a count of 1 and increment it to 2 after processing the second B. Once we've built the frequency dictionary, we iterate through the string to find the first unique character. At index 0, A has a count of 2, so we move to index 1, where A still has a count of 2. The same happens for B at indices 2 and 3. Since no character in the string has a count of 1, there are no unique characters, and we return -1 as the output. To analyze the time complexity of the solution, we break it into two main steps. The first step involves counting the frequency of each character in the string using a dictionary. This step uses a single for loop to iterate through the string. For each character, the dictionary is updated, and since dictionary operations like insertion and updating values have an average time complexity of O(1), the total time complexity for this step is O(n), where n is the length of the string. The second step involves finding the first unique character. This also requires iterating through the string, while checking the frequency of each character in the dictionary. Again, dictionary lookup operations have an average time complexity of O(1), so this step also runs in O(n). When we combine both steps, the overall time complexity remains O(n). In the best case scenario, if the first unique character is found early, the second loop may terminate early, but the first loop will always require O(n). So the best case time complexity is still O(n). For the average and worst cases, both loops need to be fully executed, which results in O(n). Now, looking at the space complexity, the main factor is the dictionary char_count, which is used to store the frequency of characters. This dictionary can grow up to a size proportional to k, where k is the number of unique characters in the string. In the worst case, if all the characters in the string are unique, the dictionary's size becomes proportional to k. Thus, the memory required for char_count is OK. To summarize, the total space complexity is OK, where k represents the number of distinct characters in the string. If all characters are unique, then k equals n, making the space complexity O(n). Let's compare this with the brute force approach. A naive method would involve nested loops, one to iterate through the string and another to check if each character is unique. This would result in a time complexity of O(n², due to the nested iterations. However, the space complexity in this case would be O(1), as no additional data structures are used. In contrast, the optimized approach we've discussed uses a single pass for counting and another for finding the unique character, leading to a time complexity of O(n). Although it requires additional space for the dictionary, which is OK, this trade-off is acceptable given the significant reduction in time complexity. Finally, when we mathematically verify the big O, the two independent passes over the string contribute O(n) each, and since dictionary operations are O(1) on average, they don't affect the growth rate. Thus, the overall time complexity is O, n, and the space complexity is O, k. When solving this problem, it's important to be aware of some common mistakes that can trip you up. First, not considering edge cases is a frequent oversight. For example, what happens if the input string is empty, contains only one character, or if all the characters are the same? These scenarios can cause incorrect results or even runtime errors if they aren't accounted for. The fix is simple: include explicit checks for these edge cases both during implementation and when testing your solution. Next, using mutable data structures inefficiently can lead to poor performance. For instance, repeatedly appending to a string in Python creates O, n squared, time complexity because strings are immutable, and each append creates a new copy. Instead, opt for efficient structures like dictionaries or arrays to count character frequencies. Lastly, avoid recomputing character frequencies inside loops. This happens when you calculate counts multiple times, either explicitly or implicitly, within nested loops. It's redundant and inflates the time complexity. A better approach is to pre-compute frequencies in a single pass and store the results in a dictionary or array for reuse. Another mistake to watch out for is assuming fixed character sets. For example, hardcoding your solution to handle only lowercase English letters might seem fine at first, but it can fail if the input includes uppercase letters, numbers, or special characters. To address this, use a dynamic approach, such as a dictionary, which can adapt to any character set. Additionally, ignoring space-time trade-offs is a common pitfall. For instance, optimizing for space at the cost of readability or time efficiency can backfire, especially if the input size doesn't justify the trade-off. The key is to understand the problem constraints and select the approach that aligns with the input size and requirements. Whether you prioritize space or time depends on the specific context of the problem. This problem is a great example of some key patterns that frequently appear in string and array questions. Specifically, it demonstrates the use of frequency counting combined with tracking the first occurrence of characters. When solving similar problems, consider breaking the task into two logical passes. In the first pass, gather all the necessary data, such as calculating frequency counts. In the second pass, use that data to determine the result, like identifying the index of the first unique character. During interviews, you might also discuss optimization trade-offs. For example, you could compare an O, n, space solution that uses a dictionary to an O, 1, space solution that relies on an array for fixed character sets. Be sure to clarify constraints with the interviewer, such as whether the string only contains lowercase letters, whether it can be empty, or what the maximum input length might be. This problem is connected to several others on LeetCode, which use similar techniques. For example, LeetCode 242, valid anagram, involves frequency counting to determine if two strings are anagrams. LeetCode 49, group anagrams, expands on this idea by grouping strings with the same character composition. Another related problem is LeetCode 451, sort characters by frequency, which builds on frequency analysis but adds sorting based on character frequency. Finally, there's LeetCode 383, ransom note, where you determine if one string can be constructed using the characters from another. All of these problems reinforce the importance of mastering frequency counting and applying it in different contexts. There are several approaches to solving this problem, each with its own trade-offs. One common method is to use a dictionary for frequency counting. In this approach, you first count the frequency of each character, then iterate through the string to find the first unique character. This has a time complexity of O, n, and a space complexity of O, n, due to the dictionary. It's efficient for large inputs but requires extra memory. Another approach is to use an array for fixed character sets. For instance, if the input is guaranteed to only include lowercase English letters, you can use an array of size 26 to store frequencies. This also has a time complexity of O, n, but the space complexity is reduced to O, 1, since the array size is fixed. However, this method is less flexible and only works when the character set is predefined. A simpler but less efficient approach is brute force. In this method, you use nested loops to check the uniqueness of each character in the string. While it's easy to implement, the time complexity is O, n squared, making it unsuitable for large inputs. The space complexity, however, is O, 1, since no additional data structures are used. This trade-off between simplicity and efficiency highlights why brute force is generally avoided for problems with large constraints, but it can still be a useful way to verify your logic for smaller test cases. Great job completing this problem. Today, we learned how to solve first unique character in a string using efficient techniques like hash maps. Remember to practice these strategies to solidify your understanding. Thanks for watching, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!